electrostatic boundary conditions are super important. Namely, they are almost your starting point. Sometimes you'll be asked to compute the potential, but then your brain should switch to asking yourself, hey, what do I need to do that? Well, so JS told me that I need to know my boundary conditions. I got my volume, I got my surfaces of the boundary. What's the boundary condition at that boundary here? So looking at boundary conditions is really quite important. What happens with electrostatic potential, electrostatic fields at boundaries. So let's just discuss that a tiny bit about what this means. And here, maybe just go back to a little bit more general discussion on this. Just actually flip it here. So what kind of electrostatic boundary conditions are you already used to? So let's imagine that you've got a surface somewhere with a surface charge density that would be sigma. So sigma is the charge per unit area. Now, one of the things that you can do first is discuss the electrostatic field. And what would you tell me about the electrostatic field on such a surface? Well, you go back to your reasonings about Gauss's law. So what you would do is you would define for me a nice little pillbox, which is a tiny little area like that, which is like above the surface, piercing the surface, and then going under the surface like this. Okay, so this is the so-called Gaussian pillbox. It's a little thing with a certain area, but no vertical dimension. You take the limit of this going to 0. The point is that the upper surface here is above the surface. The under surface of the pillbox is under the charged sheet here. And therefore, if I use Gauss's law here, what does this tell me? Gauss's law just tells me that, well, what was it again? So I've got the closed integral over my surface with the differential area dotted into the electrical field. And that has to be Q enclosed over epsilon 0. Okay, but let that area here be A. And let's imagine that I take a very, very small pillbox, infinitesimally close to this surface here. Then the field is going to be uniform over that little surface here. So what's this going to be? It's going to be just sigma times the area A, that's my Q enclosed, divided by epsilon 0. And now the point is that, again, with this part of the integral, what is it really? It's just the value of the field perpendicular to the surface times this little infinitesimal surface. Again, assuming that the field is uniform, that my pillbox is so small that the variations of E are negligible over the area covered by this. So what does that mean? It really means that if I take the electrostatic field perpendicular to the surface above, minus the perpendicular part of the electrostatic field below, that this just has to be sigma over epsilon 0. Okay, because the area cancels. Here I would just get area times value of the field, up and down surfaces. The side surfaces here don't count because I'm taking the limit of an infinitesimally thin pillbox. Okay, you've seen this reasoning before. Right, so it's all and this is a question rather than a statement, right? So yeah, question. Yes, very good question, indeed. So so here we're not done yet, yeah, because we only get a statement about the discontinuity of one component of my electrical field, namely the one that's perpendicular to my surface. Okay. So it's at least a start. It's at least a start. Okay. Now, in order to yes, other question.
Generally, I have a problem with sigma as because it's the charge of the infinitesimal small point, or that is so. Yeah, so, the area plus I really don't understand what sigma is.
So sigma is the surface charge density, namely the charge that you get per unit area on that thing. So you can make like a big blowout. Let's take a little chunk here and let's do a huge blowout of that thing. What is it? Well, microscopically, you've got a little slab of material, right, with a certain thickness associated to it. And the point is that inside this material, there are charges all over the place. And this thickness, D here, could be taken to go to 0. So the total charge that you would have in here would be, if this had an area A at the top, the total charge in there would be A times D, which is the volume, times the charge density in there. However, what we do is that we say we jam these two together. So the thickness here times the charge density, and maybe I should just like write them the other way around so you don't think this is a differential thing, right? So what do I have? I have rho times A times D, right? Because that's the charge per unit volume, and that's my volume, area here times depth here. However, we just define this as sigma A, where sigma is volume charge density times thickness of your thing. But the thickness goes to 0, charge density goes to infinity, product remains finite. So the units of sigma are coulombs per square meter. Okay? Okay, so that's the first thing. Now, the other thing that we can do is consider a line integral, which now goes like this. I do a line integral here, and I use the relationship that the curl. So I know that the curl of E is equal to 0. Therefore, the line integral, if we call this path P, by Stokes' theorem, the integral over this path P dl dotted into E also has to be 0. Okay? And that means that the parallel component of the electrical field, so parallel to any direction on the surface here, has to be the same. So E parallel above is equal to, or maybe I'll just write minus E parallel below. That's equal to 0. They're the same. Okay, and then so you see what I mean, right? So there's no discontinuity in the value of the electrostatic field as I cross this layer from just this curless condition of the electrostatic field. So we can just write these things together. And the way we're going to write it, we're just going to say that the electrical field above minus the electrical field below is just equal to sigma over epsilon 0, but in the normal direction to the surface, right? So this is the vector n hat. Okay, so that's one of the ones that you want. So in the notes, I call this equation E disk. Okay, so this is actually I should put a green thing around this, because this is an equation which I don't expect you to know by heart. I actually expect you to be able to rederive this like on a whim from stuff that you need. Okay, it's the type of boundary condition that really comes straight out of the basic equations that you know, namely Gauss's law and the curless condition of the electrostatic field. Okay, but it still gives you an idea of a boundary condition that, at least information about a boundary condition that you have. Okay, and so here, what we can do is translate this for the potential. Since we know that the potential is the line integral of the field, then we can rewrite this equation equivalently by stating that there is a discontinuity in the gradient of phi. And what am I going to do? I'm just going to use the fact that E is minus grad phi. Therefore, this equation here immediately translates to a condition that the gradient of phi above minus the gradient of phi below. Okay, it's exactly the same thing here, but just with a minus sign, right? Because E is minus grad phi. Okay, so what do we have here? You see, it's something that looks dangerously like a Neumann boundary condition for our phi, because I'm telling you something about the gradient of phi. Okay, and that's first thing that we have. Okay, so am I correct that you have written those equations in your first course as well? You kind of looked a bit at these. Okay, so maybe what we'll do in the next few minutes you'll have done, but at least so then the question becomes, are you okay with this? So here I insist. I want you to start thinking boundary conditions, boundary condition, boundary condition, boundary condition. Looking for a solution, boundary condition. Yeah. So what do I need here? You need reasoning, and the reasoning is quite simple because who are your friends? You've got Gauss and you've got Stokes. Green is your friend as well, but you don't see him very often. It's actually really, Gauss and Stokes that help you. And with those, you can come up with this kind of information. Question? Yes, here.
Yeah, so the area
That's correct. So this is what I mean by this integral here. So if I write this integral here, there would be there would be, let's call it above, and then there's below, and then there's side. So this integral here is the integral now over above, plus the integral over below, plus the integral over the side. Okay? Integral over the side is 0 because I take the limit, and there's no infinity in my field in the plane of this. The integral above, because of the size of the pillbox being so small, is area of the upper bit times the field there, which we assume to. So this gives us this term here. The second below here, now I've got the field below, but now my normal to the surface is pointing down. Therefore, E dotted into that thing, if I use conventions where E increases this way, it picks up a minus sign. That's why the second integral here is equal to minus E below times area. And then I just divide everybody by area to get this one here. So the term you're looking for is just here, this one. Okay? Okay, so these are examples. Okay, now perhaps the kind of best introduction to conductors here is as the very simplest boundary conditions you can have in electrostatics. That's what a conductor is. Question?
Got a question about the last. As the electric field above and below should be the sigma for the cancel out, and it should be 0, but that means sigma over epsilon 0.
No, the fields do not cancel. So the question is, don't the fields have to cancel? No, because of what happens because of this sigma. So this sigma, you really have to see as a finite amount of charge stacked into an infinitely thin layer. And that leads to a discontinuity in your field. Okay, in an extreme case, if you have a single layer and there's no difference between up and down, there will be an electrical field going down here and up above if you have a positively charged layer. So there's a discontinuity. As you take an infinitesimal step through the boundary, your field changes discontinuously. Doesn't do it smoothly, it changes discontinuously. Of course, physically, your real field changes continuously. But then you need to tell me details about the thickness of your layer. So this is a mathematical abstraction. Okay? The graph statement is that if you give me a layer of thickness D, then the derivative of the field is going to scale like 1 over D. Okay, so it all adds up. Is that cool? So the field has a discontinuity. But the discontinuity is just perpendicular to the surface. Okay, in the direction of the field perpendicular to the surface.